So what I would do today, like I'll talk to you hopefully in this session about the structural column. And this presentation was originally planned to be delivered by my previous student, Mahmoud Aboukifa, but he graduated only like a few weeks ago and started a new job, so he couldn't make it today to do the presentation. So that's basically the results from a recent ACI project that we completed a few months ago. And it was focusing mostly on the slender UHPC column, although we looked at other things along the way. So I will try in the next 15 minutes or so to give an overview of this project that we just completed and the final set of recommendations that we are going to propose to ACI 239C, the subcommittee on structural design, to be incorporated into a future potential, the future design guide, hopefully that the committee is working on. So the motivation, like for focusing on structural members, as many of you in the session are aware, and as you have just heard to Rafiq, the Federal Highway is doing a lot of work for bridge engineering. The ASH2 guidelines will come out soon. The number of application of bridges using UHPC is just getting more and more, and we start seeing a lot of initiatives now focusing on structural components. So if speaking of Malaysia, for example, there is a lot of going on the U-girder, and here in the US, the Federal Highway on the one hand, and the PCI, the Precast Pre-Stressed Concrete Institute on the other hand, they are championing mega initiatives for girders and UHPC flexural members. So there is a lot of work ongoing, and hopefully very soon structural UHPC, full structural UHPC members is going to be common and a popular thing to consider for the design. So we wanted to focus on columns, and since that there's a lot of work going on flexure, we wanted to focus on column with the objective. If we were to replace normal strength concrete column fully with UHPC, what would we do? So we have been working on this. We have done several projects, not only one actually or two, but we have done several to look into seismic columns, combined axial and bending, incorporating grade 60 as well as grade 100 or even higher strengths, steel. And recently we did this for slender UHPC columns, which I will share with you today. So the focus today is just to focus on the, UHPC columns, the slender ones that we have tested as part of the ACI project. So the specific objectives, of what I'm going to present today is to do experimental testing for full scale, if you will, because each of these UHPC columns, as you will see, although they are 11 inch and by 11 inch in terms of the cross section, but the capacity is close to 3 or 3.2 million pounds, which can be a full-scale column in a decent, 10, 15 story building. So these can be considered full-scale UHPC columns, and there isn't a lot, of experimental data for this level of scale that was tested before. We probably I didn't mention this, but Lafarge was our industry partner for this project. We are doing new projects that will start or started, and we have other partners as well that I will talk about briefly in the last slide. But we built several columns, 9 of them, and we grouped them in two groups. One that studied the effect of the slenderness, ratio or the height to depth ratio, and we tested columns that range from 6 height to depth ratio all the way up to 20, which you will see it in the picture. That's pretty much the largest UHPC column tested anywhere in the world to date. And then we have these the second group who focused on varying the reinforcement detailing to again calibrate the ACI equations or see if the ACI equations for predicting the design capacity is valid or not. So this was the the objective, and this is the test metrics that go with these objectives. So again, the objective is eventually to provide guidance to be incorporated in future ACI documents, based on what we have done in terms of assessing the validity of current procedure for both short and long columns in the ACI 318. So we did the construction for the 9 columns at our fab yard in Reno, Nevada. And you see, this is the columns. We did them all in a horizontal laying position to mimic precast construction, and for more convenience and to be able to do more columns. Obviously, once we had all the columns ready, we just had them in loaded to a flat bed truck, and we transported them to Berkeley. So Berkeley is 3 hours from here, and it was convenient to do the construction here and take the columns and test it there. So the test setup that we used, this is the test setup at Berkeley. So they have one of the largest axial testing machines. It's a 4 million pound machine, the capacity, and this is one of the columns that we tested here, just to give you an idea of the picture setup. So we tested all 9 columns, and you can see here these are the the damage that we got for all 9 of them. The slender ones, we did, you know, like get the damage right in the middle because of the buckling effects. For the short ones, it varied, you know, like we get it sometimes closer to the boundary conditions, sometimes in the middle. So it did, you know, like all of them, you know, like were different, but we captured the force deformation, this, you know, like relationship for all two groups. And again, this is the group that varies the, you know, like height to depth ratio, and that's the group that used the same cross section, same height, but different like rebar, longitudinal and transverse reinforcement detailing. So we can see here that the capacity, you know, like is varied a lot based on, not a lot, but varies somehow based on the detailing. But what we see more here is that the slenderness effect, that's a typical short column, you know, like if you will. And you see now as we get slender, the axial capacity drops, and we, all what I'm going to show in the next few slides, how did we went and carefully assess the, you know, like ACI procedure for slender columns, how to, you know, like estimate based on the ACI procedure the secondary moments, and the apply the moment magnification method and see if this is conservative or not to apply for UHPC. So that's one type of results that we have gotten from these tests. The other thing that, you know, like we have 9 columns, and we have now data on axial stiffness of you know, like full scale columns, if you will. So we wanted to see what, you know, like would be a good estimate for the axial stiffness. We need this for several, you know, like purposes. So axial stiffness has to do with the area and the Young's modulus of the concrete, or the UHPC in this case. So we started with the, you know, like was based like Graybeal's like recommendation. These were based on, you know, like I think, you know, like hundreds of like cylinders. So it's a lot of data, but you know, like we wanted to check if this scale is applicable at the columns scale or not. And we find that this is more like an upper bound. So we wanted to test a couple other values. So we went with 40,000 square root F prime C. We found that this is more like a lower bound. And what we ended up, you know, like finding to be the best appropriate, you know, like value to use. And we, again, this agrees with another project I did for like lateral columns, lateral UHPC columns. So we ended up now with a firm confirmation that, you know, like 42,000 F prime C square root, you know, like is, again, this is based on experimental data. So it's an empirical value based on just, you know, like the data fitting and regression analysis and so on. So that's one thing we, you know, like found from this data. And you can see here, if we use this value for estimating the UHPC, that's what we get from the estimate based on this value, and that's what we get from the test. So on average, we are almost, you know, like 1, which is a good correlation between the proposed value and the ones that we measured. Another thing that we looked at is the strains to understand, you know, like when the steel would yield, and we found in all 9 columns, almost the steel, you know, like yields around 70–80% of the capacity before getting to the capacity. So we know that, you know, like also that the concrete, like we use this to assess the bonding, you know, like to assess the later on, you know, like if there is any like buckling happen, local buckling, something happens in the rebars or not. We didn't see a lot of local buckling in the rebars. So this is not very typical, like, you know, conventional concrete, where you spoil the concrete and then you expose the rebars, you buckle the rebars and have even core failure. The UHPC, because of the steel fibers, it has a little bit different nature. So we looked at the strains as well. And like we looked at the lateral displacement, and we used these lateral displacements, especially for the very slender columns, you know, like to calculate the secondary moments associated with this specific measured lateral displacement, and see how these secondary moments would compare to what you get from the moment magnification method if you were to apply or adopt the ACI procedure. So this is also another type of results we got. And then these are just the values for it. So I'll go quickly through this. So what we wanted to do eventually, and that was the main objective from the beginning, is to assess the ACI procedure specifically for slender columns. And again, the reason, maybe I didn't mention this also clearly in the beginning, slender columns is expected, you know, like with all the superior mechanical properties of UHPC, I'm not expecting, me personally, if I'm a designer, to use the same, you know, like cross section for a conventional concrete column. Like, you know, I will use much smaller like cross section for like to take advantage of UHPC, and this is very likely will produce slender columns. That's why we wanted to focus specifically on this, and wanted to see if we were to design slender columns as per the ACI 318 provision, is this valid or not. So our goal is to assess the moment magnification method in the ACI. And to do this, it's a very long procedure. I think one of my next slides will show an outline of the procedure quickly. But one of the things that go through the procedure is, you know, like the buckling, you know, like the effective lengths for buckling. Of course, we wanted to apply this to our tested columns, so that, you know, like when we make the assessment, at least we do it based on the columns that we have tested. So we didn't want to use effective lengths for conventional, you know, like building, let's say, setting or a bridge setting where you can estimate the effective length based on other, methods. We wanted to get the actual effective length for the columns that we have seen. Then we can estimate everything accordingly. So we did, based on the buckling shape, especially from the very slender ones, we, fitted several equations, and we did like a lengthy mathematical procedure to get exactly where would be the inflection points and how to define the effective length. And we found this for our specific test setup. Again, let me clarify, this is not for a general column in a building. This is just for our columns. We found that the effective length is around 0.67. Then we were able to use this to calculate the slenderness ratio as per the ACI definition, so that we can proceed, with the procedure as per the ACI. So we did the, PM diagrams. Again, we have measure the displacements, the lateral displacements, as I mentioned, and we were able to calculate the secondary moments based on this. So we wanted to see how our, actual, force behavior, including, into account the second order moment from what we have recorded or observed in the lab, how this would fit into the PM diagrams. And we did 3 categories of PM diagrams using the actual properties with no reduction factors, using the nominal properties, and then using even the ACI procedure with all the phi factors and everything, just to see how the actual behavior, fit between these 3 ranges of PM diagrams. This was one objective. The second objective is also to see the value of the secondary moment. Again, how does it compare to what we will get from the moment magnification method? So that's one thing that we did as well. And then we were ready to proceed with the moment magnification method. Again, it's a very lengthy procedure. I'm not going to go through all the details, but the key here is that there is a magnification, factor that we calculate. And this magnification factor, depends on the slenderness ratio. So it's a multi-step process. And several things we need along the way. The, stiffness is one of them. The, EI effective, which we used for this, EI effective in this case would be some sort of a flexure one, because you are talking now about buckling. So that's, and secondary moments. So we are talking here about a combination between axial and flexural behavior. So EI effective, we found from a previous study on lateral columns that 0.7 EI cross is a good approximation. So we incorporated this. We, calculated the buckling loads, the magnification factors, and did the assessment accordingly. So these are...
Mohammed, you have 3 minutes.
Okay, so these are the results, from the magnification method. So let me get straight, to the conclusions. So one thing we did, before I get to the conclusion, we wanted to see, what would be a new proposed slenderness lower limits. And, if we were to go with the ACI definition, that this is when you start, seeing a 5% reduction in the axial load, then the new slenderness ratio will be, 23-ish. As opposed to 22 in the current code, but if we go with a more realistic one, which is a 10% reduction as per the Euro code, the slenderness, could be little higher, and then we can benefit, from this. So our recommendation will be based on the 2 values that I will show in the last slide. We did also, since we had all these data, we wanted to assess the axial load strength. So the conventional ACI equation that everyone is familiar with. If we were to use actual material properties, we wanted to test if the 0.85, which we know that this is not appropriate for high strength concrete, let alone, the UHPC, we wanted to see how bad, or how good this value would be. And we find that, this way overestimates the capacity. And we ended up again, based on our data, to propose a 0.75, reduction factor for the UHPC columns instead of the 0.85. So this is all based on the data from this. So, to wrap up in terms of, the conclusions, let me even get straight to the last slide. This is the most important one, is the design recommendation. So that's from, again, this project specifically and other projects. So we wanted to have a solid, again, this was 2-3 years of work, although the recommendation is only 1 slide. But again, this is took into account a lot of unique data, if you will. So the UHPC users of modulus of elasticity that we recommend when estimating both axial and flexure columns, stiffness is 42, Southern F prime C. That's one thing. And if we were to, have an effective flexural strength for concentrically loaded UHPC, and this actually for even flexural columns, not necessarily concentric loaded. Concentric loading in this case, because we applied this for the moment magnification method, but even we find that this recommendation valid even for pure lateral load only and flexure columns, which is the 0.7 of the gross stiffness. So that's one recommendation we have. The upper bound on the moment magnification factor, as per the ACI, is 1.4, but this value doesn't, do justice to UHPC. UHPC is much stronger than conventional concrete in flexure as well. So UHPC can accommodate larger, like secondary moments. So we recommend that this, value can be like revisited in the future. We didn't revisit this value because we don't have enough data, but we just found that this value is, conservative, and we could, use this moment magnification method for even higher values than this when it comes to moment magnification factors. Because again, UHPC has a much higher flexural capacity, so it can take, even for axial columns, larger secondary moments. Based on the ACI criteria for determining the slenderness ratio, we recommend to revisit this value to 23.5 if it's placed UHPC column, and we wanted to stick to the ACI, criteria. However, what I personally prefer is to even go with the Eurocode, recommendation. It's again, take better advantage of UHPC and increase this limit to 32, then we can, allow more and more slender columns for UHPC. And eventually, the last thing is the strength factor. We recommend this to be 0.75 instead of 0.85 for estimating the capacity. And these are the recommendation. Again, hopefully this will be presented to 239C, the structural, design subcommittee on UHPC, and it might go into the structural guide that we are working on. So my last slide, is just to bring everyone attention that we got a second ACI project, and we will focus more on the transverse reinforcement. Detailing for this, we are partnering with even more UHPC vendors, still Cientech and hopefully Kurtoff as well. So we are trying to generalize our conclusions, and make sure that every UHPC product, can be used for structural components. So stay tuned for a new project coming up soon. And with this, I would like to thank you all, and we'll be happy to answer any questions.
Thank you, Mohammed. Very much appreciated. Thanks for all the great information you shared and all the time and effort you have put into this to come to those results. Excellent. Maybe just one quick one from myself. So with all your recommendation, Mohammed, you said, for example, for the elastic modulus, the 42,000 square root of MC and the other recommendation, you mentioned at UHPC. In what strength range would you feel comfortable you're recommending those? Because I have seen in the diagram you went down to 15 KSI. So what is the strength range?
Oh, that's an excellent question. So far, most of the UHPC products that we have used for the structural components are proprietary, mixes that are, in the range of 22 to 25, KSI, maybe 20 to 25 KSI. But we are doing some work on the non-proprietary UHPCs that are still on the lower end, maybe 15, or maybe not 15, maybe 18 KSI, but we don't have the recommendation for this lower range yet. But so to answer your question, this is mostly for 20, 22-ish KSI, UHPCs. And then we will see if the same is valid for lower end type of UHPCs.